Welcome to the NMR Topicity video. In this video, I'll be going over some key terms, specifically homotopic, enantiotopic, diastereotopic, and heterotopic hydrogens, and then we'll briefly talk about axial versus equatorial hydrogens with respect to proton NMRs. So let's begin with homotopic and enantiotopic hydrogens. We'll use isopentyl acetate or banana oil as our example. Remember, this is the product of the Fisher esterification lab. So let's look at this methyl group right here. Let's say we want to examine these two hydrogens. We can do that by using the deuterium test, which says we draw both of the molecules again, and we place a deuterium on each of the molecules that we just drew. Then we simply compare these two molecules, and notice that in this case, because we can simply rotate the sigma bond, these are actually just the same molecule in different conformations. So since they are the same molecule, these two hydrogens that we examined are considered homotopic. Now on to enantiotopic. Let's begin by using the same molecule, except let's examine these two hydrogens. Let's do the deuterium test again. We draw the same molecule twice. This time we'll place one deuterium here and the other deuterium here. If we compare these two molecules, notice that we did create a chiral center, and since we place a deuterium on the wedge on one molecule and the deuterium on the dash on the other molecule, they have different stereocenters. One is S and one is R, so these are considered enantiomers of each other. Therefore, the two hydrogens that we examined at the beginning are enantiotopic hydrogens. The reason why I coupled both of these together is because homotopic and enantiotopic hydrogen pairs will give the same chemical shift in a proton NMR. So let's look at the molecule. Here we have this methyl group. Let's consider all of them as E hydrogens, and let's label these two hydrogens as D hydrogens. Notice that the enantiotopic pair will give the same chemical shift, and the homotopic hydrogens will give the same chemical shift. Now let's go to diastereotopic and heterotopic hydrogens. We'll use cyclohexanol as our example for this one. Let's examine both of these hydrogens. Let's do the deuterium test. We place the deuterium here and one deuterium there. Notice that not only did we create a chiral center here where we placed the deuterium, but since this was a symmetrical molecule, we also created a chiral center here. Notice how we have SS here and RS, so these are considered diastereomers of each other. Therefore, the two hydrogens we examined are considered diastereotopic hydrogens. Now, for the sake of completeness, I included heterotopic here. Let's use 4-ethylphenol as our example. This is the reactant for the Williamson ether synthesis. Let's examine both of these hydrogens. Let's do the deuterium test. We placed a deuterium here and a deuterium on this molecule. If we compare these two molecules, notice that these are structurally different. So these are completely different molecules. Therefore, the two hydrogens we examined are heterotopic. The reason why I placed both of those together is because diastereotopic and heterotopic hydrogen pairs will give different chemical shifts in a proton NMR. So let's look at cyclohexanol. Notice that these two are diastereotopic and they have different chemical shifts. Now let's briefly talk about axial versus equatorial hydrogens. We have butyl cyclohexane here. These values represent the ppm values, so the higher ones are more deshielded. Notice that the equatorial hydrogens are more deshielded than the axial hydrogens. This is one of the findings that made proton NMR really popular, and notice that in this one we also have an equatorial and an axial, and the equatorial one is more deshielded than the axial hydrogen.